Hi there. My name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. This semester, I've been sitting in on some lectures by my colleague Jennifer Hassler about analog VLSI design. And Jennifer showed a particular circuit that I'd never really seen before. So I'm going to put down an operational transconductance amplifier. There's an input current here into the current control pin, and then we have our usual voltage inputs, and I'm going to ground the negative input here, and then there's a voltage coming in here. And let's take the output of the operational transconductance amplifier and run it through a capacitor with capacitance C, and that's going to go to ground. Now, if I were to look at the output here in terms of the voltage and think about putting an input voltage here, this looks like a integrator with variable gain, like you might see in a state variable filter in something like the Oberheim SEM filter. But I'm not going to use it like that. So instead of V out, let me label this as just a V1 node here to make this be a little more generic. I'm going to take this voltage here, run it down this direction into another OTA going the other direction. So I'm going to assume that you'll set the current control input here so that this also has a transconductance gain of GM. Except this time I'm going to put the input into a minus terminal and we'll ground the plus terminal. So we'll take the output here and feed it back up here. And the question I'm going to ask is, what does the input impedance look like looking into the node here? So I need to create a test current source and then determine the voltage and use Ohm's law. Or in this particular case, what I'll do is I'll create a test voltage source. So let me call that VT for test, and we'll put that here. And then I want to compute the current going into here. If you're not familiar with operational transconductance amplifiers, I suggest checking out the lectures on the topic in my analog circuits for music synthesis class. So first, let's find V1. V1 is going to be equal to the current coming out of the OTA times the impedance of this capacitor, because none of the current is going into the input of the lower OTA because we're assuming that the OTA is ideal. Okay, so what's the current coming out of the OTA? Well, that's going to be our transconductance gain GM times our test voltage minus 0 volts at ground. So we'll just write it like that. And to indicate that here, let me write this. This is the current coming out of that upper OTA. All right, so we're going to take that and multiply it by the impedance of the capacitor, which is just 1 over SC. So that's our integrator kind of form. So what current do we have at the output pin of the OTA? Well, that's going to be V1 times GM. But because we have a minus sign here, we can draw the arrow here going this direction. So that's the current going in to the lower OTA. Well, there's no current flowing into the positive terminal of the upper OTA because, again, we're assuming it's ideal. So this current here, that's the current resulting from our test voltage. So our impedance is our test voltage over the resulting current. And what we wind up with, let's see, so we have VT over IT, which is GM V1. And let's see, when I plug in V1 in the denominator here, the VTs are going to cancel. And let's see, the C will go on top. Actually, the SC will go on top. So I'll have SC all over GM squared. So what does this here look like? Well, that looks like an inductance. We could say this is an inductance LS, where L here is equal to C divided by our transconductance squared. So by changing the transconductance, which you can do by changing the current going into the control pin of the OTAs, you can change the effective inductance seen looking into the circuit here. Now, this has a name. This is called a gyrator. But the way I'm used to seeing a gyrator is with op amps. Here we have a gyrator with OTAs. And using OTAs gives us a level of flexibility that we don't have using standard op amps. Now, this is the way that Jennifer drew the circuit, and this is typically how you would use it in an integrated circuit design from what I understand. In a PCB level design, we might want to throw in some resistors here to make sure that we don't have too much voltage going into the OTAs, to make sure the OTAs stay in their linear range. So let me put a resistor divide down here and one up here. And to avoid having current going through here, we should also put some buffers here. So let me put a voltage buffer here, and I'll put a voltage buffer here. So that could be an op amp with the output tied to the negative input. And in terms of what you would do with those resistances in the formula over here, you could just fold the effect of the divide down ladder here into the transconductance gain. Now we have a voltage controlled inductance. Well, technically speaking, the OTAs are current controlled, but of course you would have some sort of voltage to current converter that's feeding those. You will often see gyrators used in place of regular inductors in equalizer circuits, like in this Boss HM2 heavy metal pedal. And I think it would be interesting to replace such op-amp-based gyrators with OTA-based gyrators, even if you don't change the control current going into the OTA. You could deliberately goose the hyperbolic tangent nonlinearity of the OTA and effectively have an inductor with nonlinear characteristics. Whether or not the resulting nonlinear inductance in any way resembles the nonlinearities you find in real-world inductors, I have no idea. If you have any insight about this, please leave a comment below.